Okay, let's get started. Welcome to the RTOP July 2025. Um, Congratulations to everybody who uh, ran the Eastern Conference. It was a very well. I'm getting a lot of good input on that. Got a lot of good new pictures that I'll put in the next journal. So it appeared to go very well. And congratulations, everybody. Um, the we'll have a board meeting on the probably the second Sunday of August. That'll give Tom Jacobs some time to get all the books done since July is our end of our fiscal year, and so he can get all the books wrapped up by then, and then we can have a good treasury report for the board meeting. If you were elected and you're on the board, you are officially now active. But I do want everybody from the past board and the current board to go to the board meeting. So we do have Brian, who's our new secretary. He's on. Do you got anything going on, Brian? Caught him off guard. Okay. Caught Brian off guard. Okay. So, and since Robert just sat down and he's the farthest time zone person at 4 in the morning, Robert, what do you got going on?
Just in process, nothing new to report. I'll be out at the observatory in a couple of weeks and try to get you some data for the Southern Hemisphere. I'm assuming you want is Ezra data as opposed to the 3D printing, 3D imaging data. Is that correct?
I do.
Well, well, I knew that part of it.
Robert, we'll take everything. Anything you want to give us,
You
we'll
know,
take on display.
I have terabytes and terabytes of data. Do you really want it? But
I'll
not the
just wrap
data
it
that
up
you're
into
talking about.
a nice paper presentation. That'll be fine.
Sounds like a plan.
All right,
All right.
great.
So anyway,
Okay,
so nothing new to report.
all right. Thank you very much. Uh, let's see. Let's go to Edward.
Hello, hello. Can you hear me?
Yes.
Great. Yeah, so I've been quite busy lately, actually. So I'll share my screen if that's okay.
You got it.
Um, see. Okay, and now I want to put this in presenter mode. Yes, there we go. All right. So yeah, maybe those of you who have been looking at the forum recently have maybe noticed this project of mine, but I've been working on something along the lines of radio recombination lines. So yeah, I think most or probably even all of this group are familiar with the well-known D hydrogen line at 14 to the 20 megahertz. So the spin flip transition of neutral hydrogen. But in fact, there are many, many more spectral lines in the radio spectrum, even from the hydrogen atom. However, many of these spectral lines are, of course, very weak and are probably not possible to detect with typical small amateur antennas. So a couple of years ago, I encountered a report by the Astropilot group. And what they did was they had a whole observation reports on radio recombination lines towards various star-forming regions in the galaxy. And they did this with a 25-meter dish at Astropilot. And up until that point, I had never heard of radio recombination lines, and maybe you haven't heard about them either. So I'm going to give a very quick explanation. So yeah, essentially, when we have a hydrogen atom, it of course has the electrons around, or the electron around a hydrogen atom can have certain energy levels. So you can see this in this little diagram over here. So what happens if we have a ionized hydrogen atom? And it encounters an electron, and this electron recombines with the hydrogen nucleus. So then, yeah, this electron, this will end up initially in some very high energy level, and it will slowly decay into lower and lower energy levels until it reaches a stable state. And in each step, so from each step from a higher to a lower energy level, it loses energy in the form of a photon. So this, of course, gives rise to the well-known emission spectral lines. So those of you who are into optical astronomy are probably familiar with the hydrogen alpha line, which is one of these transitions between some of the lower order energy levels, where the energy gap is quite large. So the spectral line ends up being in the optical part of the visible part of the electromagnetic spectrum. But if you look at the very high energy levels, so the energy gap is so small that the spectral lines end up being all the way in the radio spectrum. So those are the so-called radio recombination lines. So there are many different radio recombination lines. So I've included a small table here of some radio recombination lines of hydrogen in the L band around the hydrogen line frequency. So there's quite a few of them, but yeah, in terms of observational properties, they differ from the neutral hydrogen emission in quite a few ways. So first of all, radio recombination lines, of course, require ionized hydrogen. So you only find them in H2 regions where there's ionized gas. So, and there's of course only specific patches in the sky. So you can't just detect a radio recombination line in any direction. You really have to specifically target a certain H2 region. And the second property that makes them difficult to detect is that they're very weak. So over here on the right, you can see an observation from the AstroPilot report. And what they did is that they pointed their 25-meter dish at the Orion Nebula for an hour or so. So this is one of the brighter sources of radio recombination lines. And yeah, here you can see this is the H166 alpha line, and there's a carbon line as well that's even fainter. But these lines are, this H166 alpha line is only about 0.25 kelvins. So if we were to observe this with a 3-meter dish instead of a 25-meter dish, so the surface area of the 3-meter dish would then be about 70 times smaller. So the signal level would also be 70 times weaker, or in other words, it would be only 4 millikelvins. So that's basically undetectable. So recently I encountered another interesting paper from the 1980s, and it included a map of the H166 alpha radio recombination line emission towards the Cygnus X region. So Cygnus X is an interesting region in the sky. There's a lot of star forming regions in a small area. It's also a bright continuum source that can be easily observed with a 3-meter dish. And yeah, as you can see in the map, the radio recombination line emission is not particularly intense. It's not one of the strongest sources, but it's very widespread. So you can see that I've drawn here a red circle representing the 5-degree beam width of my dish. And you can see that the recombination line emission would essentially almost completely fill this 5-degree half-power beam width. So in this particular case, if we were to observe this region with a 3-meter dish, just the beam filling could at least partially compensate for the small dish size. So just guesstimating from the map, I thought, well, I could be maybe receiving like 50 to 100 millikelvins of line intensity. So this would, of course, be quite hard to detect, but it's within the realm of possibilities based on my earlier experience with observing galaxies at 1420 megahertz. So yeah, I decided to give it a try with my 3 meter dish. I have presented about the system before, so I'll try to keep it short. But essentially, I have a modular 3 meter dish, so it's 4 segments that I can assemble together whenever I'm in the mood for some observations and when the weather is good, of course. It has a W2 IMU type feed for 1420 megahertz. Then there's a G8 FEK L-band LNA, followed by a bandpass filter. I had to retune it a bit for this project because I had to retune it towards some of the RRL frequencies. Then there's a second amplifier to overcome the cable losses, and then there's finally 10 meters of cable to the shed where I have an AirSpy Mini SDR running connected to an old laptop that is running SDR Sharp with the IF Average plugin. So yeah, this is a stationary dish, so I just it's just manually pointed. So I just doing everything in drift scan mode. And Jason and I have both come up with an approach to detect faint spectral signatures using only drift scans. So yeah, we've told about this before during earlier RTOP meetings and also during the Western and the Eastern conference this year. But just to give a very quick summary, so we are just basically recording for several.
Yes, sir, I'm in a meeting. No. Yeah, if you could. Yes.
When the target passes through the beam, and then I'm averaging a block of spectra when the target is passing through the beam. So these are my on-targets. This is my on-target spectrum, and then I also take 2 blocks of spectra before and after the transit of the target, and I subtract those from the on-target result to get rid of the SDR bandpass response. So initially, I was having some troubles with temperature stability because when the temperature changes, not only does the gain of the SDR and also the LNA change, but also you get a slight change in the spectral bandpass response, and that, of course, can really screw up your spectral results if you're looking for these very faint spectral lines. So I made an attempt to at least somewhat stabilize the receiver chain. So ideally, you would stack everything in temperature-controlled boxes, but I don't really have the means or the motivation to do so. So what I just did is that I just wrapped the LNAs and the filters and all the other outside components in insulation material to at least slow down the temperature changes. And I initially mounted the AirSpy Mini SDR, as you can see in this photo on the left, on a heatsink, and this heatsink was hung into a big tub of water, which acted as which of course, like, it takes a lot of time to heat up and cool down water, so it's kind of stabilized the temperature, and that worked really well. But of course, it's not ideal, especially not for long-term observing projects. So I eventually just put the SDR on a big block of aluminium, and that also worked quite well. So initially, I was targeting the H166 alpha line because that was the line that was also mentioned in the paper that I just discussed. And also, it's very close to the hydrogen line at 1424.7 megahertz. But unfortunately, I was running into some troubles with some very persistent RFI spikes at this exact frequency. So later on, I switched to H167 alpha at 1399.4 megahertz. And there I had still some RFI, but at least it was not like exactly at that frequency. So that was more manageable. So in total, I recorded about 9 transits. So I just let it run overnight for 9 days. And yeah, first I just looked at the continuum. So I just averaged all the spectral signals together and then plotted that against time to see what it looks like. And you can see this very nice bump that is always occurring at the same right ascension. And yeah, when we compare that to a radio map, you can see that it matches up with Cygnus X in the galactic plane, which is a strong, basically a group of strong continuum sources. So there's these star-forming regions that I was just mentioning. But if you look closely, there's also a slight bump at 20 hours in right ascension, and that matches up with the Cygnus A radio galaxy. So and because Cygnus A is only a few degrees apart from Cygnus X, you can't really fully tell them apart, but you can just, with a 5-degree beam width, see just a slight bump from Cygnus A. So, of course, this has all been done before, so it's not a very big surprise, but it's still really nice to see. So then up to the radio recombination line. So yeah, this is the end result I got after averaging these 8 drift scans. So you can see there's a sharp dip at minus 100 kilometers per second. This was from a persistent RFI spike at 1400 megahertz. But there's also this broad peak that's rising just above the noise, centered at around 0 kilometers per second. So this is at the expected frequency. And yeah, it also matches up with the paper that also mentioned that the LSR velocity of the radio recombination line in this region was around 0. So there was some deviations towards like plus 10 or minus 10. So this is looking quite promising. And on the right hand side, you can see another version where I reduced the resolution and I also fitted a second order polynomial through the baseline to the background and removed that to get rid of some of the residual slope. So this is all very interesting, but yeah, is this really the radio recombination line, or are we just looking at some particularly persistent RFI? So one of the first checks I did is to see if I could recover the RL signature from the individual transits, and I've plotted those here. So let's go back one slide. I plotted those here. So on the vertical axis, you see the time. Horizontal axis, you see the LSR velocity. And you can see that at least in 6 out of 8 transits, there is a very faint signature at around 0 kilometers per second, as we would expect. So then I checked, okay, is the signal only present towards Cygnus X? So what I did is that I also did the whole same analysis, but for a patch of the sky that is well away from Cygnus X. So at the right ascension, that is 1 hour before Cygnus X. And as you can see, no RRL-like signal was detected there. So yeah, so far this is looking quite promising. So yeah, what's next? So of course, I would like to do a write-up of these results in the SARA journal, maybe do some further analysis, try to do some Gaussian fitting to derive the line width and the velocity. Compare that with results maybe from others. Ideally, I would also do some further observations, but currently the weather is quite bad, so I cannot set up the dish right now. Yeah, and what is also very nice to see is that my thread over on the forum sparked quite some interest from other observers. So some other folks have also done their own observations. I believe, yeah, Dmitri is also here in the meeting, so he will also probably present about his observations as well with the Skynet dish. Okay, that was it. So, are there any questions?
That's fun results. Thanks very much. I'm fascinated by how you set up your dish and then take it down. You say it comes in 4 petals or sections, and then I suppose the focus is separate. How long does it take for you to set it up, let's say?
Yeah, it depends. It takes about 1 hour to 1.5 hours, so it's quite a bit of effort. So I only set it up like once every few months, and then I just do a observation run of typically a few weeks. So I really try to get the most out of it.
Magnificent and quick work, I guess. Thank you.
Are you planning on doing observations, say, of the Orion region, or is that maybe perhaps that signal won't be visible because of the smaller area that's emitting?
Yeah, I think it's the latter case. That is just Orion is just too small. So the only reason I think I'm able to get away with detecting radio recombination lines in Cygnus X with the 3-meter dish is because it's just so extended.
Hi, it's Mark here. If I can ask a question, your 3-meter dish, I noticed it's a mesh. It's not what do they call it? Like a grill. Is that right?
Yeah, it's a 3 millimeter aluminium mesh.
That's because I'm relatively new to this subject, and I purchased this Noelec 1.4 gigahertz, 100 centimeter, and it's like a grill. I wasn't aware that mesh would give a better performance. Is that true also for the H1 line, which I'm struggling to try and observe at the moment?
Well, actually, if I think about it, so if you have a grill, so just essentially these are like parallel wires and
Yeah.
strips of metal. So if the polarization of your antenna is like 90 degrees twisted with respect to like the direction of these grills or bars, then essentially like it's this it should be a reflector because like yeah, it's a bit difficult to explain. So I hope you understand what I mean. But yeah, as long as like your polarization angle is like at the right angle with respect to the direction of the grill, then
Right.
there shouldn't be like too much leakage.
So is it a dipole antenna, the receiver part? It's a
Yeah, it's yeah, the antenna type. So it's essentially like a monopole in a waveguide, but it's also linearly polarized. So
right. Okay, I don't really understand much about the ins and outs of monopoles, dipoles. I just see that the receiver on some dishes looks quite sophisticated. I did take the Noelec apart just to see what was underneath that plastic housing. I just need to read more about this. Thank you for your explanation.
You'll get there.
Yeah, thank you.
All right, any more questions? Excellent, good work. That's new stuff for this group. Keep it up. Okay, Dmitri.
Oh, Girish, thank you. Edward told very well about recombination line. I'm here with similar topic. Just a moment. Okay. Do you see the screen?
Yep.
Okay. This is also observations of region in Cygnus X. Is DR21 is part of Cygnus X, and observations by using 20-meter Green Bank dish Skynet. Mm, you can see a picture of infrared picture of Cygnus X, the right in the right of the screen. It's very colorful, beautiful picture of this region. This is a very huge regions, and can feel can feel a beam of small single dishes, like of Edward. It's his idea that weak radiations from weak radiations can be absorbed by when the source is filling the dish almost fully. DR21 is a part of Cygnus X, a smaller part, but its size also can fill the beam of larger dish, 20 meters. So weak radiations, weak lines can be detected well with from the parts with larger dish. This is star forming region of Cygnus X complex. High features high infrared luminosity observed. Also, H2 spots can be seen by observing recombination line of hydrogen. Also, hydroxyl and other molecular clouds can serve as traces in star-forming regions. Here is infrared spots from DR21. You can see short infrared and long infrared and even millimeter waves pictures. Form of DR21 is elongated in far infrared band, and here coordinates and picture centers are in molecular and maser activity area, and this activity is coincide with far infrared cluster, as you can see in next picture. You can see upper part is here is far infrared, a group of far infrared spots. Here in the top parts of DR21, very high infrared luminosity, about 10 and 5 solar luminosity, many H2 spots detected. This is ionized hydrogen, distance about 2 kiloparsecs. You can see again brightness map of Cygnus X. This is a full map, and DR21 region is somewhere here. So is here. You can see size of beam of 20-meter dish here. I located the beam about the maximum of recombination line expected and observe it here. DR21 is the brightest part of Cygnus X. I observed somewhat other line, other recombination line, H166 alpha. Its frequency is close to well-known spin flip hydrogen line, and initially it was confused with this recombination line, 4024 megahertz. Initially was confused with this spin flip hydrogen line, 4020 megahertz. For 20-meter dish, the beam filling factor is about 0.76. It was calculated in assumption that the source and expected antenna temperature also not too high, 0.15 kelvins, 150 millikelvins. Here aperture efficiency for this is sorry, this is not aperture efficiency, this is main beam efficiency. For 20-meter dish calculated from known aperture efficiency, 0.6. As you can see in instrumentation characteristic of this dish, 20 meters, 1.73 degrees in observed recombination line, somewhat narrower in hydroxyl lines, frequencies, 0.6 aperture efficiency, as I already told. Main beam efficiency is 0.8. Measured system temperature measured in this May, calibrated in this May, two values from Cygnus A weight band calibrations, 60 and 62 kelvins, and corresponding system equivalent flux density, two values of system equivalent flux densities. Details of calibrations, I wrote about details of calibrations in last issue of the journal. And you can see the details of calibrations there. And my results for H1666 alpha line. Here you can see raw data, just raw data from Skynet, and integration time is 200 seconds. Here is using Skynet, there is limitations in integration time because of longer observations, longer integration times requires more. It's more expensive in credits. And the cost of these observations I've made 200 credits is not too small. Is not a small value. For now, reminder of credits is about 1,500 credits there. tracking observations, high resolutions mode, 2024 channels, resolution and velocity is about 3.2 kilometer per second for this line, and here result of of average of two polarizations. And antenna temperature was calculated to the brightness temperature of the regions. You can see my brightness temperature is about 50 millikelvins, one half of Kelvin. Velocity is about expected. 0, maybe a bit faster. 0. Calculated with system temperature 60 kelvins from calibrations. I am not. I can admit that this system temperature is somewhat overestimated. It is and can lead to overestimation of brightness temperature. But I have observed also hydroxyl line 1665 megahertz. Yet its level, it's about expected 5 Yansky in level. I've got 6 Yansky in level of 1665 megahertz hydroxyl line from DR21. So integration time is about 200 seconds. And the beam filling factor for this reconnaissance is, and I would note the beam may not look strictly to the hydroxyl radiation maximum of DR21. It may be a bit different. Max of recombination line and max of hydroxyl lines from DR21. Next observation is 1667 megahertz molecular line. This line is not radiation, but this line is not radiation observed, but some back off from background level. This is absorption line. Same integration time and resolution of receiver. Here the resolution and velocity is less than 3 kilometer per second. Also average from 2 polarizations. Scale of this plot is recalculated to brightness temperature of DR21 regions in assumptions that hydroxyl cloud has the same size as H2 cloud of ionized hydrogen. This is not very rigorous calculations. It's for only for some estimations of the absorption in temperature units. It's some back off about 0.4 kelvins of absorption to background level. I say thanks. This is all for now. If some questions, I will be glad to answer.
Any questions for Dmitri?
I have a question, Dmitri. I didn't quite catch the OH line emission that you had observed also to do the comparisons, and then the absorption. I'm just trying to think of how were those two being observed. One being the emission line, and the other one the absorption line.
Emission line here is only recombination line and hydroxyl 1665 line. Absorption line is not connected with emission line, but I used a temperature scale only for some only to estimate back off to only to estimate a back off from background level. This is not quite strict, but some estimations. This is can be seen as separate observations. It's okay.
But both were for the same region, correct?
Both are from the same regions, both from same point. So hydroxyl and max of hydroxyl point may not coincide with recombination line maximum. I aimed only in these observations. I aimed only recombination line, and hydroxyl observation is some additional results from DR21.
Great, thank you very much.
Okay, any other questions? This is a great, you guys are teaming up really nicely on these recombination lines. Okay.
Okay.
That it? Okay, Andrew. Andrew, you there?
My apologies, just finding the audio button. So sorry about that. So I mean, the one thing I would like to show tonight is something I put into the chat, is to do with my Muon detector dashboard. So I'll just show that now. I mean, how do where have we gone? Share screen. Okay, let's do that. Right. So I've got this, well, over the last 2 or 3 weeks, I've posted this link, but it's been some modifications occurring as time goes on. So this is what I think is likely to be the final version of it. So just to remind people who either might not know or have forgotten, so this all relates to detecting muons using some cosmic watch muon detectors, a project developed by MIT. And hopefully a little picture will come up here and show you 1 or 2 of them. So here's one, and here, the blue one here is more like what mine looks like, similar sort of idea. So it has a piece of plastic in it, which is like 5 by 5 centimeters in size and about 1 centimeter thick, and this is doped with some other substance, which I'm not sure what it was, but that makes it so it's more likely to scintillate. That's give off a little flash of light when it gets hit by a particle such as a muon or an alpha particle or a beta particle. And then you have something called a SIPM, an SIPM, which I forget what that stands for. It's basically a little microchip attached to the side that can act as a detector and very sensitively pick up these little flashes of light. And then you use 2 of these, one on top of each other, which helps you to distinguish muons from other things like alpha and beta particles. And then you can measure them and count them up. And it's a brilliant project that MIT put together. They claim you can do it for £100. That's if you can get hold of the components easily. Perhaps cost a little bit more in reality. But a group called the UK Radio Astronomy Association, which is a charity here in the UK, have been producing them, which makes it a lot easier to get hold of them. And although it's a great project, what has been less great is having any method of actually collating and displaying the data. And so this is where this dashboard comes in and provides a range of different ways of mapping it. You can actually change very easily on the sort of the number of days. So it says 2 days. I can change it to 7 days, supposedly. This is where embarrassing it'll work. There we are. By time range. And what you'll see is you don't see very much because I haven't actually collected data over that time period. But you can change when the data's there, you would be able to see it for as long as you want it. So let's go back to just today. So 6, where are we? June 6. Just speak amongst yourselves. Come on, come on, come on. Yeah, a bit more like it. Sorry about that. Back to the last 2 days there. So it tells you. So this is actually collecting the coincidence data. So this is where the two detectors are working in harmony with each other to just detect muons. And I can see that on my setup here, I'm detecting 0.1689 counts per second. This is over since I turned it on a couple of days ago, 36,000 muons that we detected. And you can see the various things per minute, per hour, etc. USB 0 is just the port that's being used. This first graph is the one that tells you really the main thing, which is mapping out the muons, and they change over time. So the hope is if I come back to that in a few months, I might see a point where the muons particularly went up or down, and might be able to correlate it with something. Here, this second graph has presented similar data in a different way, which is it's collated the data in 5-minute intervals, sort of like binning it over 5-minute intervals, and then it's added up all the muons for the whole of the 24-hour period and said, well, what percentage of those occurred in any given 5-minute period? And so you can see it's all relative to a 0% on the y-axis. We've got the next one I don't quite understand. A guy called Miguel has actually wrote this, which is done an excellent job of it, but I don't entirely understand all of his graphs. So I've given an attempt at the top here to try and give an explanation as much as I could get hold of it. But this is a similar sort of thing, but looking at it in a slightly different way, presenting the data. And then you've got the different frequencies of when the muons occurred, etc., etc., and some of the different. And the bottom, these are actually looking at measurements coming straight off the detector itself in terms of detector performance and estimating how far the muon must have traveled through the detector before it was actually stopped. So various bits of information, some less useful than others, but a rather nice, colourful way of presenting the data and easy to explore by changing the amount of time you're looking at to try and identify when major events or even when there's like a collection of muons occurring together, which might indicate a celestial event of some description. That's me done.
All right. Any questions for Andrew?
I apologize for the noise in the background.
I didn't hear it. All right. Thanks. Bob, you have a muon detector setup you're doing.
Yeah, that's correct. I'm still working busily away on it. I've got a bunch of printed circuit boards that I've built and put components on. Now I'm writing software and just not at the point yet to start really showing it. I want to see it actually functioning. I'm trying to build about 6 of these things, so I'd have 3 operating systems. And I'm making progress, but I'm just bogged down now writing code for the Pico actually, this is like a project that has sub-projects. And the sub-project, one of them is to have a motion control system using a analog devices sensor that will monitor a magnet. And so you can come up with the degrees that you're pointing something. And so I'm going to publish that too also, and people might be interested in that for dish pointing. But that's the part of it I'm working on right now, actually. So that's very interesting software that Andrew showed. The challenge in these projects is to figure out how to analyze your data and get something useful out of it in the long run. And so the Edward and Dmitri both have spent a lot of time analyzing data and done a nice job of presenting it there too. I enjoyed seeing that work. So I'll eventually post all this on GitHub, and if people are interested, they could duplicate some of the things I've done.
Okay, thanks, Bob. Jason and Lisa.
Yeah, so I actually spent some time on, I believe was it Thursday, Andrew? Yeah, it was Thursday that we met up. And Thursday evening, afternoon for me. But we managed to get another galaxy observation out of the 20-meter dish. And so I was just going to kind of show that. So let's see here. Let me share my screen. Where is it? Share. Here we go.
Realize you are.
All right.
We're getting very choppy video from you. So just realize that.
Oh.
Audio is fine. Just the video is a little slow. There you go.
Yeah, it's my HughesNet internet service. The only service I have available here is at my location is a satellite. So there's a latency, which is really annoying, but it's all right. Let's see here. So let's do this.
You got it.
So can everybody see that? All right.
Yep.
I'm going to minimize this and all right. So we decided to try to take a look at M104. It's the Sombrero Galaxy. It's one of probably out of all the ones that I've observed so far, it's the one that's most edge on. And again, we used the same type of settings, L-band with high resolution and on off. I can't remember how long of a duration. It was at least 200 seconds that we did. Because this one was getting down there in brightness, but you can see, you can just make out a spectral profile that's centered around 1,000 kilometers per second, which is according to the info I looked up, the heliocentric radial velocity for the Sombrero Galaxy is just over 1,000 kilometers per second. So you can see that it's kind of centered on that. And it's pretty wide. It's several hundred kilometers per second wide, and that's because it's nearly edge on. So the spectrum is spread out quite a bit by the Doppler shift. And so yeah, that's pretty much what I have. So anyway, I hope that was something kind of quick, but it seemed like the whole last couple weeks there's been a lot of problems with the 20-meter dish. It was offline, on and off, and it wasn't working. And I reached out to Green Bank a couple of times, and just to see what the status was. And then it was actually while Andrew and I were meeting on Thursday, he noticed that it was back up. So we went ahead and did that observation live while we were actually talking. And then I did a quick analysis while we were on our Teams meeting, and then I kind of pulled it all together this afternoon right before the meeting, so I could present it. But anyway, that's what I've got for today.
Great. Any questions?
And I finally made it out to New Mexico. So, good. So yeah.
All right. Okay. Thanks to you guys. Ted.
I'm just fascinated by what everyone's doing, getting ideas, slowly working on a better feed, and setting up another antenna up in Estes Park, Colorado this time. Busy with so many projects. No news to report. Eager to see what other folks are doing.
Okay. Thanks, Ted. Adrian.
Just amazed at some of the reports on today. Just really fantastic work. I really have nothing to contribute, but boy, it's just some fantastic stuff that people are doing. Just trying to get myself worked up to being able to get equipment up for observations, and still working on that. And so that's kind of where I'm at.
Okay. Thanks. Helen.
No, just sitting here, paying attention, seeing what more I can learn. That's it.
Okay. Are you still suffering from your scorpion bite?
Yeah, we're doing better. Now we got the flu. We're in a very small town. When one person gets sick, pretty much the whole town gets sick. So, but we're getting there.
Oh, okay.
Thank you. Bye-bye.
Don Latham.
Hello, everybody. Hope this is coming through. I don't have anything new except I did find out one thing that a lot of these remote weather stations are using satellite telemetry at 1.6 gigahertz in that band. So don't be surprised if you're looking for OH I think that's OH, that you will find that you might be picking up some local interference from those stations. Other than that, nothing new.
Okay, thanks, Don. Paul.
Hello, am I getting through there?
Yep.
All right, yes. So I have a little bit more of a review of some of the work that I did that I presented the last meeting. I was able to get on to.
Okay.
Let me see if I can get the sharing working here. Let's see. Let me know if it's coming through. And
not yet.
Am I up and running?
No.
No. Okay. Let's see if I can figure out. Hold on a second. Sorry, this is always tricky, I'm afraid.
Coming up. Now we see it.
All right, good. Okay. So what I am doing is trying to continue validating some of the work that I had done before. I'll just do a quick presentation of what the previous work, and what one of the interesting bits of feedback I got, it was Wolfgang pointed me towards this website that had a database of information collected with some big telescopes, and it had this rather nice feature where you could, in addition to picking a coordinate, you could even have it simulate a smaller dish. So That's what I was using to try to see if I could validate the results from my what I call a raster study. I just, to be clear, I don't know if it's really a raster per se, because I don't have the antenna continuously moving in a zigzag. I have discrete points that I sampled. So maybe it's better to call them mosaic. I don't know if it matters, but just to clarify that detail. Just to go back over what I did was, I'm using the little new electric antenna that was that I mounted on a Celestron telescope mount, and I wrote some software to move it around, and I used IF average to collect the data. To point the dish, what I do first is I have a little guide scope that I mount, and I can very accurately point to the target, and then I remount the radio antenna, and I have it mechanically set up so that it's on the same axis and it's pointing to the same point. So what I do is I have a software package that I call Raise, which I wrote in Java and Python combination, that lets me do the analysis of the data that I've collected. And this is just gives a little idea of the summary. This is just a lot of information I have about the coordinates for each point. What I did was I collect a 7x7 matrix centered around some point, like, for example, centered on, say, the center of the Orion Nebula or Heart, or various things. I'll show a few of them. And so I have the coordinate information and the time information and so on. And last time what I showed was that I go and I collect this data and do a bunch of analyses on it. I can take time windows and pseudo color it and create two-dimensional maps. This is about a 30 by 30 degree area that I'm capturing using just a 1 meter antenna. And the top row there, you can see are various types of displays of that data. On the middle right side is a heat map where I just took all of the frequency bands that I covered, just add them together and just get a heat map of it. So I have different ways I can view the same data. This particular one happens to be Orion. Orion centered. I'm not claiming that I'm actually picking up Orion with a 1 meter dish. So what I did was I went and I used that website. I'm not really sure what the right thing to call it is. It's this. I don't know if you can see this red URL here. It's called HIS survey site, HI survey site, right? I guess that's the best way to refer to it. So what I did was I went and I manually put in all the coordinates in my grid, and I configured the thing to return results of what it would look like with a 1 meter dish. And I got these plots, and I thought that was pretty nice, and I was able to do some comparisons, but not of the amplitude, because when I generate these plots automatically, it normalizes them. So you can't really do a comparison of the amplitude. So I was talking to Alex about it. I said, Alex, is there, do you know of a way that I could automate bringing this data down? And he said, well, why don't you just look at the code of the web page? And sure enough, I was able to do that. And I was then able to to semi-integrate it into my application and actually go through and have it download this matrix of information in a form that I could then read back into my program. And so this allowed me to show the results. Is this big enough? Can you see these graphs, or is it too tiny?
We see enough to start with. Give it a try.
Okay, so what we have is on the left side is my data, and on the right side is the corresponding data from the server. And so I was pretty encouraged by the results, that they're in the right ballpark. Not only are the amplitudes matching fairly well. The upper right corner of my data, the left side data, is off because I had noise there, so I got rid of that data. But overall, it was pretty good. And not only is the amplitude in the right ballpark, but more important, that the shape of the peaks was correct, or I should say matched what we're getting from the survey site. So I was pretty convinced that I must have actually gotten real usable data, and it's not just artifact. So I was rather happy about that. And I repeated it for some others. This one here, this is was centered on Cas A, and once again, it was pretty good. I mean, especially since the shapes of the curves are in the right ballpark. And what else do I have here? The Crab Nebula centered, I did, and I think I maybe have one more here. I'm not sure if I got it or not, but yeah, I have this one here. This one is the Heart Nebula. And so, overall, it's not a perfect match, but I was, pretty happy that with a 1 meter dish and all the noise I had to deal with, that I actually got something that was, looked like it was kind of lining up. So, thanks to a bunch of people helped me, Alex and Ted, and of course Wolfgang, to point me in the right direction for figuring out how to do this validation. Just one other little quick thing, which I don't entirely understand, is that Alex had showed me this data that was centered on Orion, that was done with a large telescope at high resolution. It was a raster scan, and it doesn't. The frequency was slightly different. I don't really quite understand why the shape is completely different. Maybe somebody can explain that to me. That I certainly can understand why I couldn't pick up a little structure like that with a 1 meter dish, but I would have thought maybe it would look a little bit more like something in the middle there. And as I said, that my data did match what the survey site simulation was when I did it at the matching resolution. So just one little thing. And the other thing I think I found was on that that survey site was this. I think someone had done this with the Crab Nebula with I think it was maybe a 3 meter dish they did this with, if I'm not mistaken. And so that was ballpark like mine is, let me see if I can find a better example. So it's kind of in the right ballpark. So anyway, so, I was pretty happy that I was able to at least convince myself to some extent that I was making some progress with this. So I guess that's it for now. I'll turn it back to you if anybody has any questions.
So I don't have a question, but I think I have a little bit of an explanation for your question as to why the raster scan with the higher resolution looked totally different than yours with your lower resolution. Those raster scans, spatial raster scans, are looking at continuum power. So they're looking at the entire background going up or down as you scan across the sky, where what you're looking at in your data and also what the lab survey data is showing is narrow spectral information. So it's not the whole background moving. It's not like a broad continuum source. It's actually a spectrum that's an emission line spectrum. So you're looking at narrow band sources. So you're looking at basically two different things.
Okay, well, thanks for that.
All right. Wow, excellent work.
One
Anybody
more
got any
question.
questions?
I see a real nice 3D graph up in the top right. What creates that?
So what I do is I've integrated GNU plot. GNU has an interactive plotting system, and what I do is I just dump a file out of my Raise software, and I have like an automation in Java. So I dump the file, and then I actually run a GNU script that generates this, and it's like some of the other things that I've seen people present. You can actually rotate it around and rescale it and all this stuff dynamically. I didn't write that piece of code. It's some elegant thing that someone else or some other people developed, and I just cut and pasted that image into my presentation slide here.
Very nice. I like all this exploration. I'll go check out GNU plot. Thanks.
Any more questions? Wow, excellent work. Keep it up.
Thank you.
Okay, Abel.
Hi, everybody. I am new here. This is my first time in this meeting. I'm learning what you are doing. I am a professor of astronomy and astrobiology at the University of Puerto Rico at Arecibo. I did theoretical work and also research at the observatory, and I'm trying to move to a smaller scale with small telescopes. In our research right now, I am going the other way around. So in my research now, we are exploring the Wow signal. We have the new data, and I mean data from the whole telescope, Big Ear telescope. We have most of the data now, and we are combining that data and getting new insights. And we put a paper last August 15, yes, August 15 for the anniversary. And we have another paper this August with new results about that science, new science and new data about the Webb signal. But we are also doing this project to build a small telescope. And that's how I got interested in what SARA is doing for a long time. Because my experience in hardware is very limited. So anyway, we are trying to create this network of small telescopes with working together as one to explore the sky, to search for transient events, any transient events at all. That's what we're looking. And trying to make a recipe of a kind of telescope that everybody can buy. Nothing that anybody needs to solder or be technician to assemble, just off the shelf that we can use for science and we can use also for outreach. And that's we're working on that right now, and I'm testing a system now for a month, testing stability R5, and I'm trying to use the software. We're writing the software in IDL. Plus, I have now some students that once everything for analyzing the data is correct, then they will translate it to Python and something to run in a Raspberry Pi, and that's it.
All right. Well, what do you think about all the stuff, the recombination lines, and all the stuff everybody's doing with the small dish?
Oh, that's totally amazing. That's totally amazing. I never thought about using small telescopes, and now when I see what all of you are doing, I just got amazed. I just what I didn't did this before a long time ago, but yes, is something that. Probably, for example, in our system that we are creating, maybe is the science that we're doing, but there's so much science and software that people from SARA and others had already done to also maximize this small radio telescope. That this is amazing. I love it.
Great, great. Well, invite all your friends to the Zoom meetings and get them to join SARA, and then get the journals and everything. So
we are planning
to. glad to have you, and come back.
Please. Yes, thank you.
All right, thank you. Okay, Ken Redcap.
Yes, sir. The main reason I joined today was I wanted to start thinking about SARA West 2026. And just to get the word out, I'd like to go to Stanford, but that's, I've got to work out a few things. But that was the main reason. I just wanted to get the word out there because I realized we just finished SARA East. And well, Sarah West comes next. So
Right.
I'm just getting the word out, but that's what I'm thinking right now. I was kind of hoping Dave might be online because I know I'd be tapping him. He's out in Hawaii, correct?
Right. He's not online yet.
No, he's not. He's not. But that was the main reason.
Okay. All right.
So
So we're thinking Stanford, everybody.
yes.
All right. Okay. Thanks, Ken. Let's see. Brian O'Rourke.
Hello, everyone.
Hello.
Hope everyone's well. Not much going on here. I just poured some concrete blocks to make a base for what I hope to be uh, uh, a set of small telescopes using the scope in the box antennas, and then a couple of the dish antennas. And my goal is to place them all on like a 4x4 fixed. So I'll be doing some drift scanning. And I can only do drift scanning because there are lots of huge trees around, so I don't have a very broad range of sky. So I'm just going to do that. And then I'll be running the feeds to a combinator. So I'll only have one, what am I saying? One wire going into the computer. No interferometry, in other words. It's just going to be combined signal. So it'll be a bit stronger, but lower bandwidth or band spread. Uh, Let me see. I think that's about it. Let me see. Oh, my Super SID, I wrapped it up in some uh, I'm sorry, I'm forgetting words. I wrapped them up in pool noodles, you know, the little swimming pool noodles, and they have a hole in the middle. So I cut them in the length and I run it over the wire to protect the wires because you know the wire is very flimsy and weak. And I've had my Super SID antenna on the inside of the house, but even though there's not much signal degradation, there is some. So I want to put it outside and see if that uh, improves that signal. Uh, and that's it for radio astronomy. Uh, and Rich, I did send an email to the leadership group regarding getting access back to the thing so I can help Tom with the treasury stuff. I don't know if you could communicate that to the
Oh yeah. Chip can shift you on there. I just
yeah. I'll send Chip an
look
email
at it.
then, and I'll get that stuff going back. And
All
that's
right.
about it for me. I don't have any fancy slideshows, and I'm just happy to say you guys are really peaking too soon. Slow down and no, I'm just messing with y'all. That's it. That's it. Y'all have a good day. Bye bye.
All right. Thanks, Brian. Our new secretary, everybody. Okay. Preston. Can't hear you, Preston.
I don't see Preston muted, but the circuit is not working. We don't hear you.
Okay. I'm gonna skip until you get that, Preston. Mark, did I get you already? I think I did. Mark
Right,
Wynn.
sorry, I'm here. Yeah, sorry, I've not got really anything to add. I'm still setting up my my Noelec dish. I built a kind of mast to attach it because I've got very limited space where my dish is, so I need to raise it up about 10, 12 feet so it sees above the greenhouse and the garage. I've got one question though about time. Sarah, these 200 seconds that these guys had on this Green Bank 20-meter dish, how is that managed? The time allocation for I mean, are members allowed to submit observation requests to Green Bank?
So I can field that if you want, Rich.
Go ahead.
So SARA has an account with the University of North Carolina in Chapel Hill has a program that they call hilariously Skynet. And most of the telescopes that are on that system are optical telescopes for astrophotography. But the 20-meter scope at Green Bank is the one radio telescope asset that's on that system. And SARA has an account on that system, and SARA as an organization purchases credits, so many credits I think they do it every 6 months right now. And so that they have a contract with Green Bank and with the Skynet system. And so if you contact Steve Zekas, he's the one that manages that, our side of that for SARA, and he can get you access to the SARA login and password, and then you can access it and queue up whatever observations you want to using that website, the Skynet website. So.
Right. I'm certainly not ready to submit any sensible observation requests yet, but I mean, 200 seconds sounds like a very long time. I did read about Skynet, and I saw people were taking like 1 second observations, but maybe that was with the optical scopes. Yeah.
No, you're correct.
No, you're correct. Yeah, in fact, that was a lot of those were mine and Andrew's. We were trying to map some of the brighter galaxies in Doppler using the hydrogen line spectra. And because we were doing a whole bunch of points, we wanted to really conserve how many credits we were using. So we were using the minimum amount of time possible that we could still get a decent spectrum, so that we could kind of be thrifty with the credits. In the case of this last observation, M104, it's a very weak source, and so it took more time on target to get enough signal to get anything useful.
Okay.
You usually do pulsars for like 1 to 2 seconds. So, and those are pretty weak, but good scope. Yeah.
Hey, where is it that one can find the tutorial for the 20-meter telescope? So people are interested in that, by the way.
Actually, I did one, and also Steve did one on YouTube. Look up the 20-meter on YouTube. We both did one. His is more detailed, and mine's more, running through a couple examples. So yeah, I'd try those first, and they'll get you. We did a bunch of pulsars and other things with those. And by the way, if you guys want to produce one, if you find those lacking, you can produce one too. And we got enough experts now in the 20.
I know I did. Yeah, I think like a year and a half or so ago, I think I did a tutorial on how I do the galaxy observations and the data analysis for that.
You did, and it was really good. So I think everything's on YouTube. We just got to figure out how to find it and get everybody
link
to
it up.
Reference it, yeah.
It's almost too much stuff. Okay. All right. That all you got, Mark?
Yes, thank you. That's great. Thank you. Cheers.
Doing good. Let's see. Jay Wilson.
Well, hello, everyone. I really enjoyed today's presentation. So thank you, Edward and Dmitri in particular, Jason always, but good presentations. And I hope this will inspire everybody to do similar things in the future. I always just take a back seat to my friend Ted locally, And so I'm not contributing a lot, but I just stand back and sort of applaud what he's doing at our local observatory and now remotely up at Estes Park. I guess the one thing I do have to add is I put in chat a link to some of the photographs that Chip Suffici and I took at SARA East. The film camera photos within the restricted zone were all by Chip, and a few of the others were mine. So in the chat, if you want to download those pictures, they'll be there for about another week. So now's the time to get them if anyone is interested. There's also, I'm not sure how this happened, but there's a video from last year of Jason giving a talk in Drake's Lounge. Absolutely not sure how it got embedded on the camera, but it was dated this year and right there. So I went ahead and loaded it anyway. I'll figure out the technological glitch later on, but it was not posted to last year's conference, but it's there this year. The other thing, sort of a troubling note, National Science Foundation has published in the Federal Register their budget for the coming fiscal year, which begins on October the 1st. The published version shows a complete shutdown and mothballing of the Green Bank Observatory with a $3.3 million annual budget for shutdown and mothballing. Shutdown and mothballing of the solar observatory at Kitt Peak and several other very, very important NSF projects that are deemed lower on the priority list than others, such as ALMA and the VLA. And while I think most people in the science community would support the priority list that NSF has come up with, the basic problem is the drastic cut to the bottom line budget of NSF, which from a personal perspective, I would say totally guts the American ability to continue high-level science for the next year. Very, very discouraging. It has been published. I'm not sure there's any debate that's open at this point. Seems the decision has been made. I spoke this week with staff at Green Bank. They have been encouraged that they will not be completely shut down as quickly as one might think, but I used to do federal budgeting for a federal agency, and I understand the seriousness of any agency saying they're going to shut down and mothball a facility. And that's the official story at this point. And any further questions, I guess one can address to senators and members of Congress. Sort of seems to be out of the hand of the scientists at NSF. And as a result of all this, the director of the National Science Foundation has resigned. So that's all I know on the subject, and I wish the story were more positive.
Well, thanks, Jay. Yeah, hopefully we could pick up some of this slack if we can. We got some grants that maybe we can give out. Okay. Dennis Hoofnagel. Okay, Dennis, I'm not hearing you. No, not hearing you, Dennis. let me go back to see if I get Preston. Preston, are you back on?
Preston sent us a text. He can't talk.
Okay. All right. Sorry.
He's got a project and he will show it to us when the time comes.
Okay. Johnny Cox.
Hey there. Can you hear me?
Yes.
I just have some Radio Jove. Not much to say other than yesterday was the first post Jupiter conjunction that I received radio signals from Jupiter, and it was a good IOB storm, and that it's exciting for me. Just to let you know what I have in my backyard, I got a terminated folded dipole square array. And that's really all I've got to report.
Do you got any output or anything you could show us what it looks like?
I unfortunately not, but maybe the next time I will. But I have it all, but I'm not prepared to show it in public as of right now.
I get it. Yeah, just think about putting together a small observation report for the journal. That'd be great.
All right. I hadn't considered that. I don't consider me in South Carolina being of that to do that, but I'll consider it from here on. But thank you.
Yeah, I don't have enough Radio Jupiter observation reports. I'd love to have some more.
Okay. Well, it's all on one computer. I've got everything I've ever recorded, and it's recording 24/7 now.
Great.
Got it. It's all on there. I just got to go get it. But thank you.
Oh, thank
So
you.
can I ask Johnny a question?
Oh boy.
You have four folded dipoles, is that right, in a square?
It's a square array, folded dipole antennas in a
And
square
how
array.
big is one side of the square? What's the
25 feet.
Yeah, and what resistance do you have on the folded dipole where they come together on the back side?
The resistance.
Do you remember what the resistor value is?
No, I'm sorry.
Okay. I was just curious. Okay, well, thank you.
Hey, Bob, why is that important?
Well, it sets the impedance of the antenna, and the value that's suggested on one about like he's got is 600 ohms, I believe. And it creates a 600 ohm folded dipole. And I've had other hams tell me that they've done this and got better luck with an 800 ohm resistor. And I've got the same scenario set up. I only have two sides of my square in place right now that I've been collecting data with, that I've been monitoring WWV and the frequency change or the Doppler shift in that frequency change due to the ionosphere movements. And I want to improve the signal if I can. And I was just curious what he had.
So Bob, how would you, if you measured that, would you just measure that with a voltmeter and?
No, you'd use like a vector network analyzer or the inexpensive little nano VNA. And what I did was I built a ladder line that was supposedly 600 ohms, and then I have a balun that's kind of like a transformer that does a conversion from 600 to 50 ohm. And I think I have a lot of loss there. So I built one of the PC boards that I built, it's another project, is a differential preamplifier to put at that antenna to like mount it right on the dipole antenna and then send the signal back to my data collection system over a 50 ohm line, and therefore eliminate the ladder line and the balun, and hopefully get an improvement in my signal and bandwidth.
If he had to increase or decrease the resistance, is that adding more wire or doing, what do you
No,
do?
you're just changing the resistance on the folded dipole is a wire that goes in a kind of like a bow tie. And on the back side, you tie the two ends together with this 600 ohm resistor. And then on the other side where you connect to it with the feed line, you connect whatever impedance line that you end up with. There's in the ARRL antenna manual, this is discussed in there, and you can find a section that explains all that.
Johnny, are you using RG6 on your
No,
on the Radio Jove?
I use RG57.
Okay. Same
Yeah.
thing.
Dave Topinski would be the person, that's where I got that antenna, would be the one to answer questions that you may have where I can't even come close. But that might be a person, and you know, you can contact me and I'll get you in touch with him because he's a wealth of knowledge of all of this that I am not. I just enjoy looking at the screen. It was yesterday was middle of the day, real-time observation of that, and that's soon it will be in the middle of the night, so I enjoyed the daytime part.
All right, great.
A quick
Thanks,
question.
John.
Quick question. I thought the folded dipoles, kind of like the old analog TV antennas, were 300 ohms impedance. Where does the 600 ohm come from?
If you're asking me to answer that question, I'm not sure I have the ability to do so. Maybe others would.
Well, the impedance of the antenna is going to be dependent on the length and the spacing that you put between the two wires. And so it's a characteristic of the layout of the antenna. So the old TV antenna was probably set up for 300 ohms. And yes, it used twin lead 300 ohm wire.
So are these like dipoles in series, or I was just trying to figure out how the 600
I
ohms
don't
came
know
about.
how his is configured, but I have two separate dipoles that are orthogonal, and I'm monitoring them individually. So my goal was to try to get phasing information from the signals.
Okay.
You may have them set up in a different way because they try to look at the radio Jove signal as a wave, I think, in the way it strikes the two different dipoles depending on the spacing.
Yeah, I think that's correct, but I'm guessing at it. But it's kind of a loop. Each dipole antenna, there are four of them. They came from Dave. Dave built the antenna, and it came in the mail, and I put it up per his instructions. And there's phasing cables with it that I can that are outside in a box at the antenna.
So is the orientation kind of providing directionality?
It does, yes.
I see.
It's you know, the settings of the compass, north, south, east, west. And then you can put a different length phasing cables to adjust what the antenna sees, if that makes any sense.
So is that kind of like sort of like for circular polarization, where you're using the phasing cables to get that 90-degree phase shifts, or?
No, I don't think it's circular polarization. I think what you're doing is just trying to enhance the reception of a wave by picking the parts of the wave that you want on the antenna based on the spacing.
The Jupiter is different altitudes in the sky, depending on the time of year and the time and the year. So what they're trying to do is they're trying to get the phasing of two dipoles so that the max reception is angled at where the Jupiter is supposed to be when it crosses. So it's really a pointing, helps you pointing these two dipoles with the phase cables. That's why he's got new other phase cables, because like next year it might be higher or lower in the sky as it crosses, and he's going to have to change the phase cables to get the better angle for that maybe next year. So
Yeah,
that's what they're doing. That's
basically a very, very simple phased array.
right.
Okay, great. That makes a lot of sense. I appreciate it. Thanks.
All right. And yeah, Radio Jupiter is one of my first antennas systems I did, and I had all sorts of fun trying to match the signals coming out of it with the prediction software. It was a good, really good starter. Okay, thanks. That was good stuff.
Thanks.
Bill Cheney.
Hi. Good afternoon, everyone. I'm just enjoying learning as much as I can by hanging out with you all on this Zoom. Appreciate it.
All right, no problem. Are you trying to get a antenna set up, and where you're located? And
I'm in Chula Vista, which is south of San Diego. And yes, I am going to be setting up an antenna here in the near future.
all right, and are you on the forum?
I am a member of SARA. Which forum do you mean?
Oh, the SARA forum.
Yes, I am.
Okay, yeah. Just keep everybody up to date on that, and they'll give you all sorts of help setting up your antenna.
Oh, okay, great.
Say, Bill, hi from Mira Mesa.
Oh, hi. Yeah. Yeah, we've got good weather right now.
Fantastic. Yeah, just perfect. Envy of the whole country.
Adrian, I lived in Mira Mesa for 2 years, so I agree with you. All right.
You have to pay for it, but I'm telling you, it's worth it.
Yeah.
Oh yeah, no kidding.
The fires don't get you. Yeah. Okay. I think that's everybody. Is Dennis or Preston able to get your comms up?
Yeah, I'm here. Can you hear
Oh,
me?
Dennis, go ahead.
Yeah, I'm sorry. I changed things around, and then suddenly my microphones were trying to work on something else. Anyway, nothing to report, but I've really enjoyed the reports that have been given. Just great stuff, and it just gets all the fluids flowing and the gears working. Lots of fun.
I
So
know.
thank you.
Yeah, everybody's doing really well. Okay, thank you for Preston. You able to come up yet? I guess not. Okay, I think that's it. Did I miss anybody? All right, 2 weeks, Drake's Lounge. Everybody, thanks a lot. Good work, everybody.